Hi, I'm Andrew Tomazis, and this is an introduction to ISO WG21 D2288, which is an extension for C++ designated arguments. So this presentation summarizes section 1.1 informal tour of WG21 D2288. So we're just going to give an introduction to the functionality. Only the functionality is presented here. If you're interested in the motivation, requirements, design process, the formal specification, and so on, please see the full paper. So let's dive right into an introductory example. This example shows off a few of quite a number of the features, but it's not exhaustive. But it's just to sort of get a feel for what's going on. So here we see a class color with two constructors. It has both constructors have 3 parameters, and the types of the parameters are float. So the first thing we should observe is that this normally wouldn't work, right? Because they've got the same number and type of parameters. It would be an error on the second line because it's a redeclaration, but it does work. And the other thing that's unusual here is these colon characters after the thing, which we'll get to a bit later. So somehow these two constructors do work. Okay, so standard vector of color V, and then we're calling in placeback. And normally in placeback you give it the arguments and it will forward them to the appropriate constructor, right? But in this case we're putting these identifier colon things in front of them, and these are called designated arguments. And so what we're sort of showing off here is that the designators are forwarded to the right constructor. So you see one of the constructors has blue and green parameter names, and so it's somehow in placeback is selecting that correct constructor. Also notice that the arguments are in a different order to the parameters. So green and blue in the parameters, and this is being passed as blue and green. Okay, and also notice that red is being defaulted in this first call, and red is not normally. That wouldn't work either, right? Because red is not at the end of the parameter list, right? And in placeback is doing something similar, but it's using brightness, so it's calling this second constructor. Okay. All right. So let's build up to that stuff. Okay. So just point on terminology here. Function declarations have parameters. So this is called a parameter. Function calls have arguments. These are called arguments. We call this a positional parameter. If it doesn't have an identifier and a colon, it's a positional argument. This is called a positional argument, and then this is called a designated argument. So x:42 is a designated argument. So a designated argument can be written like this, or alternatively it can be written like that. Both are equivalent. They mean exactly the same thing. And in a similar fashion, designated initialization of a struct of an aggregate class type. Here we have S with one member. You can write it like that, .x equals 42, or you can write it like that, and again, they're equivalent. Implicit designator. If a designated argument has the same name and value, so here we're calling a function f. The designator has the parameter name is x, and the value we're passing that parameter also happens to be called x, as in it's an ID expression X, you can just omit the name like that. Okay, so now we go on to parameters. There are three kinds of parameter. Positional parameters, like that. Designator optional parameters, like that. And designator-required parameters, like that. The way to remember that syntax is think about these dots like a little bar graph. So 0 dots is positional. Think no amount of designation. 1 dot is designator optional. Think low amount of designation. Like the designator is optional, so it's like a low amount of designation. 2 dots is designator required. Think high amount of designation, like the designator is required here, so it's two bars, right? Anyway. So as you would expect from the names, so positional parameters only match positional arguments. So here we have a positional parameter, and we pass it a positional argument, and that works. We try to pass it a designated argument, and it doesn't work. Designator-required parameters only match designated arguments. So that's sort of the opposite of that. So here we have designator-required parameter on the end here, and then we pass it a positional argument, and it doesn't work. But if we pass it a designated argument, it does work. On the other hand, designator optional parameters will match either. So we have a designator optional parameter here. You can pass it a positional argument, or you can pass it a designated argument, and they'll both work. Designator optional parameters only match arguments in the same position. So here we have two designator optional parameters, X and Y, but we try to call them in a function call with Y and X, and this is an error because designator optional parameters have to be in the right position, like positional parameters. Designator required parameters, on the other hand, match arguments in any position. So here we have two designator required parameters, X and Y, and we call them in Y and X order, and that's okay. Designator required parameters last. So designator required parameters have to come last in the parameter list. So here we see this function f has designator required parameters. It has 1, and that's at the end, so that's okay. Here, this function f has a designator required parameter, but it's not in the middle. You know, they're not at the end, so that's an error. The parameter kind and parameter name are part of the function's type. So for the new parameter kind. So here we have a function f with one. Here we have a function f with one positional parameter. So the fact that this parameter is positional is part of the function type, but not the name, because positional parameters don't have significant names. So the type of this function is void taking an int, as usual. Okay. Now we have a function f with designator optional parameter called x. Its type is void of parameter designator optional a parameter named x. So both the fact that it's designator optional and its name x are part of the function type. Here we have a same situation with designator optional parameter named y. The fact that it's designator optional and y is part of the function type. Same with designator required and x. Designator required and x is part of the function type. Designator required parameter y, then designator required parameter y is part of the function type. And it's important to understand that all 5 of these functions are different from one another. So these 2 functions are different because they have a different name. this function and this function are different because they have a different parameter kind, and so on. So designator-required parameters are an unordered part of the parameter set. So what that means is that the order of designator-required parameters are not part of the function type. So here we have a function f, takes designator-required parameter x, designator-required parameter y, and here we have a function g that takes designator parameter y and designator-required parameter x, but f and g have the same type. That is, the function types designator-required x, designator-required y, and designator-required y, designator-required x are the same type. Okay? So it's, put simply, it just means that designator-required parameters, the order of them is ignored. The declaration order of them is insignificant. Okay, so external local parameter names. Oh yes, so parameters can have different external and local names. Normally a designatable parameter has the same external and local name, but sometimes it's useful to separate them, and you do this with a slash. So here we have an example of a function definition returning int f designator-required parameter, and its name has identifier slash identifier, really long name slash x. This first name, the really long name here, is the external parameter name in this example, and x is the local name. So the function is written in terms of the local name, x, but this local name is not visible outside of the function definition. Only the external name becomes part of the type, so the type of f remains void designator-required parameter named really long name, and when you call it, you still use the really long name. So this is a function call to this function. Again, it doesn't use x; it uses the external name. So you can actually use this. You can omit this slash local name to indicate a parameter is intentionally unused. So normally, for a positional parameter, you can just comment out the parameter name, but that no longer works because the parameter name is significant with designatable parameters. So to replace that technique, you can put a slash after it and just leave the local name empty. This indicates to the compiler that you really didn't mean to use that parameter. Okay, so because of all this function type stuff, you can now overload on parameter name and kind, actually. So here we have two overloads, like we saw in the first example, where the parameter name that differ only in parameter name for designatable parameters. And if I call this function f with x, then overload resolution will pick the first one and it will print 1. And then if I call it with y, then a designated argument with designator y, then it will call the second one. So how does overload resolution work? So, well, let's just go through in general how overload resolution works. So the function name is looked up to return a set of functions with that name called candidates. If any of them are function templates, they get instantiated into functions. And so we have a set of candidate functions. Functions that are not viable are discarded. So there's a bunch of rules. It looks at the argument list to the function call and to at the parameter lists of the candidates, and there's an algorithm that says which ones are viable and which ones are not. So any ones that are not viable are discarded, and then the remaining viable functions that could be called by those arguments are ranked based on a ranking algorithm and to find the best one, and then the best one is called. If there's no best one, then that's when you get an error ambiguous function, ambiguous function call error. Okay, so designated arguments mainly alter the viability phase. So we discussed before about what kinds of parameters match what kinds of argument, and we've seen this table before here. So if the arguments don't match the parameters in this function, then in this fashion, then the function is not viable. Simple. And plus, there's the added pickle that designator-required parameters can be matched in any order. So basically, yeah, I mean, logically, you consider every possible order of the designator-required parameters, but obviously the algorithm is just to sort them or some. There's a fast implementation of this matching, but right. If the arguments don't match, then the candidate is not viable. So a positional argument is a better match to a positional parameter. Yes. So in ranking, there is a one ranking rule basically that a positional argument is a better match to a positional parameter than to a designator optional parameter. So here we have a function f with a positional parameter. We have a function and another overload with a designator optional parameter, and we call it with a positional argument f42. It selects one. Without this rule, it would be ambiguous, right? But it selects one, and this second call with a designated argument selects two, right? Because the designated argument is not a viable match to a positional parameter. So you can use this. This is used to overload like that without. I mean, you could use the designator-required parameter here, but then you would lose the position sensitivity, which is important in some use cases. So, okay, so a designated argument is an equal match between a designator optional and designator required parameter. Yes. So if you overload designator required with designator optional, you can't. I mean, it's ambiguous basically. So here we have a designated argument, and it's not a better match to either one of those. Yeah. Okay, so default arguments. This is a parameter with default argument. As we should know, you put equals 40, equals expression after the parameter. That gives it a default argument. So if you call it and you omit that that argument, it will pass the default. It will pass 42 to x. Okay. So designator optional parameters have the same default argument rules as positional parameters. So nothing's changed there for designator optional parameters. Designator required parameters have different default argument rules, and they're better. If a function has designator required parameters, then only they may have default arguments, right? So here we have a function. It has some designator required parameters. Only the designator required parameters can have defaults. You can't, if we try to default the non-designator required parameters of this function, it's an error. Okay. However, any subset of the designator required parameters can have default arguments. So here we have two designator required parameters, X and Y, but the first one has a default and the second one doesn't, and that's fine. Well, I mean, as we discussed before, designator-required parameters don't have a significant declaration order, so that shouldn't be too surprising. Okay, so any subset of arguments to designator-required parameters with default arguments can be omitted. That's very cool, right? So we've got a function here, f, it's got 3 designator-required parameters. We can default or not default any subset of them, as we saw in the introductory example. Yeah, similar to the introductory example. This designated argument z is setting the last parameter here and then defaulting the first 2. Normally we couldn't do that with positional arguments and parameters. Okay, so forwarding designated arguments. Right. So designated arguments can be forwarded. So here we have a struct S with a constructor that takes a designator-required parameter X. Okay, and we can call makeUnique of this struct and pass X, and makeUnique will forward it on to this thing somehow, which we'll go through. And then we've got a vector here of SV, and then we can place back, as we saw in the introductory example again. So this is just forwarding. And it works with designated initialization as well. So we have aggregate class type S, and we can forward the designated arguments onto designated initialization of that, and same with, place back here. So the forwarding mechanism is part of sort of the designated argument generic programming sort of system. So we introduced 2 new keywords, decalarg and forward arg. So let's dive into the code to forward a single argument. So we take here, we're writing a function f that forwards its argument, perfectly forwards its argument to G, including any designators. So the template, the code for that's not highlighted is the normal code for that, and the highlighted code is what you need to add to make it designator aware. So the template takes a type template parameter designator in addition to the arg, the normal arg one, and then you have the parameter arg, and then you add an external name for that parameter using forward arg of that type template parameter, and then that deduces the designator from the argument, and then to forward the designator, you, rather than identify a colon, you put forward arg and then the designate this type template parameter colon, and then the normal standard forward arg. Okay. So the type that actually was getting deduced was called a designator type. So there is a new family of built-in tag types called the designator types. Every parameter in the language has a designator type associated with it. So a parameter has its normal type, its parameter type, and it has another type as well. It has its designator type. Okay. So all positional parameters have the same designator type called the positional type. So there's one type called the positional type. There's one tag type called the positional type, and that's it. But the designatable types are more complicated. So for every identifier X, so we're using X as like a placeholder here, all designator optional parameters with the parameter name X are associated with a designator type called the X designator optional type. So if you have a designator optional parameter that's called foo, then the designator type associated with that parameter is called the foo designator optional type. Same story for designator required parameters. So designator required parameters with parameter name x are associated with a designator type called the x designator required type. So basically, a designator type encodes the parameter name, the parameter kind, and for designatable parameters, the parameter name. Okay, so there's a declarg specifier. You pass it a parameter name, and it will give you the designator type associated with that parameter. So decal type will give you the type of the parameter. Declarg will give you the designator type of the parameter. So here we see an example. We have a function f. It has a float parameter that's designator required. Its external name is omega, and its local name is z. So if I say using t decal type of z, you'll get float, right? Because that's the type of the parameter. If I say using d equals declarg of z, you'll get the designator type associated with that parameter, which in this case is the omega designator required type. Okay. So forward arg specifier. Okay, the forward arg specifier takes a designator type as input and outputs a parameter or argument, basically. So given a designator type D, to use forward arg to produce a parameter, you just use this forward arg specifier of D in lieu of its external parameter name and its parameter kind token here, the dot or the colon or whatever. So the parameter, and it will create a parameter such that D is the associated designated type with it. So if D is the positional type, then this will be a positional parameter. This will just be like index. If D is the foo designator optional type, then this will be a designator optional parameter with external name foo. Okay, and so on. Forward arg specifier. So given a designator type D, to use forward arg to produce an argument, you just put the specifier in lieu of the identifier in a designated argument. So here we call a function f. This is a function call now of f with a designated argument, and the identifier is a forward arg of D. So if D is the positional type, then this is equivalent to a positional argument, f42. So if D is the positional type, then this is just a positional argument and doesn't have a designator. Otherwise, this is equivalent to a designated argument with the parameter name D. So if D is one of the is a designator required, one of the designator required types, or one of the designator optional types, then it has a name associated with it. So the designator optional designator types and designator required designator types have a name associated with them, right? And this argument will just become that name. So for example, if D is the foo designator optional type, then this is f of foo 42. If D is the bar designator required type, then this is f of bar 42. Okay. So if you pass a type template parameter to forward arg in a parameter, then it deduces the designator type from the argument. Okay, so we can pass a designator type to D, and it does what we said it does before, but now we're passing a type template parameter to it rather than a designator type. And what will happen is that when this function template is instantiated, the instantiations parameter kind and name will be based on the argument that is passed. So if f is called with a positional argument, f42, then D is deduced as the positional type. The instantiation's type is void int. Right. If f is called with a designated argument, f alpha 42, then D is deduced as the alpha designated optional type. The instantiation type is void int dot alpha. Oh, you can't see that, but yeah, it's the alpha designated, then void int dot alpha. Yeah. Okay. Where were we? And you can also use forward arg to decompose function types. So normally to decompose a function type, you define a primary template with a type template parameter, and then you write a specialization of that for function types. And then if S is instantiated with a function type, then it will use this specialization and it will decompose the function type here, right? And so the stuff that's not highlighted is just that normal stuff. Here we're just, for the sake of this example, we're only doing void returning functions, but you know, there's all kinds of ways it could work. But the important thing here is that we've created another pack along with the parameters pack args. We've created another pack called designators, and these are going to hold the pack of designator types from the function type. There are, you know, the designator types associated with its parameter list, and that's just the syntax here to use forward arg here, and then designators will be deduced. So take an example, an instantiation of this S with this function type here, positional, you know, this function type here, deduces designators as the 3 type list, the positional type because of that, the Y designator optional type because of that, and the Z Designator-Required type because of that. And that's how we implement things like stood function to be designator aware, is so that they can deduce these designator types out like that. Okay, so that's a quick introduction to the functionality. As I said, please have a look at the full paper. It's yeah, it's quite lengthy, I know, but I think it's if you're interested in the background and the design process, then do so. If you have any questions or comments, you can mail me directly. That's my email address, or you can hit me on the WG21 EWG reflector. Okay, all right. Thanks, guys. Bye.